Welcome to the deep dive. Today we're digging into some really interesting material you sent over, notes, articles, a paper abstract, all pointing to something called Next-Frame Diffusion.
That's right. And our plan is to really break this down, figure out what next frame diffusion or NFD is all about, how it actually works, and maybe most importantly, what's new here? What are the technical ideas they're bringing?
Yeah, and the big promise seems to be generating video not just well, but fast. Like real-time fast. Fast enough for interactive stuff, maybe streaming. That sounds like a pretty tall order.
It absolutely is.
So let's start there. Why is generating good video frame by frame in real time such a tough nut to crack? What are the technical roadblocks the sources mention?
You've hit the nail on the head. Getting realistic, smooth video out instantly, well, it really pushes what current AI can do. The sources flag two main bottlenecks. First, you've got the, and I'm quoting here, high computational costs associated with diffusion sampling.
Right, diffusion models, they're great for quality, images, video, but that sampling, that whole refining from noise thing, that just eats up processing power, doesn't it?
Exactly. It's like, think about sculpting. You start with, a block of noise, basically, and you refine it step by step, iteratively, chipping away until you get the final clear frame.
Okay.
Each of those steps, each chip, needs a lot of calculation. And you have to do that for every single frame of video, maybe dozens of times per frame. It adds up incredibly fast.
And you need, what, 30 of those finished frames every second for real-time video? Okay, yeah, I get that. What was the second bottleneck?
The sources also bring up hardware inefficiencies inherent to autoregressive generation. So even if your model is designed to create things sequentially, one after another,
Which makes sense for video.
right. But the way these complex networks run on hardware, like GPUs, sometimes there are gaps. The hardware isn't always working at full throttle, especially when generating frame by frame in that strict sequence.
So it's like the processing cost inside each frame is high, and then making the frames follow each other smoothly on the hardware adds another layer of inefficiency.
That's a good way to put it. Those two things together, the cost per step and the sequential hardware use, that's why hitting true real-time speeds, 30 frames per second, maybe more, has been so incredibly hard for high-quality AI video.
Right.
You could get quality or you could get speed, but getting both at the same time, especially for ongoing arbitrary length video, that's been the challenge.
And maybe we should pause here. Why should you, listening now, care about this chase for real-time video? What does it unlock?
Well, the sources mention this directly. Real-time video generation isn't just about, watching AI cartoons faster. It's about enabling truly interactive experiences.
Okay.
Think about applications where the video isn't pre-made, but generated on the fly, reacting to what you do, what you say, maybe even how you're feeling.
So like training simulations that adapt instantly. Or maybe virtual characters you can actually talk to in live video.
Exactly. Or even virtual worlds built around you as you move through them, that kind of potential. The sources also specifically call out supporting streaming applications with arbitrary duration.
Ah, so not just short clips.
Right. A lot of current models generate fixed length videos. Real-time autoregressive generation means you could have a stream that just keeps going, adapting as it goes, perfect for maybe live broadcasts or personalized content feeds. It shifts video generation from being like batch processing to something live and responsive.
Okay, that makes sense. Now, the sources talk about two main flavors of video models, autoregressive and bidirectional diffusion. What's the core difference and why does one fit this real-time ongoing thing better?
Yeah, this is really key to understanding why NFD is built the way it is. Let's think about how they build the sequence of frames. An autoregressive model, like the sources say, generates frames sequentially.
One after the other?
Yep. Frame 2 is based on frame 1, frame 3 is based on frame 2, and so on. It only looks backwards.
Following times arrow, basically.
Exactly. Now, a bidirectional diffusion model, it also uses that iterative denoising, but it can, and this is the key part, often consider information from both past and future contexts.
Future context, so it kind of peeks ahead?
In a way, yeah. It might refine frame 5 by looking at frame 4 and maybe some information about what frame 6 is likely to be.
Okay, so it has a wider view, but why is that less suitable for real-time or streaming?
Well, the sources point both out. Because it might need that future context, you often have to define the whole video length up front or process it in big chunks. You can't easily just start generating frame 1 and keep going forever, reacting instantly if the input changes because you don't know what's coming next.
Right, because in a live stream or an interactive game, you have no idea what the user will do next second or when the stream might end.
Precisely. The input could change anytime. So autoregressive models are just fundamentally better suited for these cases because they only need the past. They generate sequentially, making them great for arbitrary duration and real-time scenarios.
Okay, so that brings us right to Next-Frame Diffusion, NFD. The sources call it an autoregressive diffusion transformer. So sequential, using a transformer. What's the specific architectural trick they mentioned that helps it be efficient while being sequential?
They highlight something called blockwise causal attention. Now, causal tells right back to what we just said, it's autoregressive.
Only looks back.
Right. When generating a part of a frame, the model's attention only looks at previous frames and maybe earlier parts of the current frame, respects time.
Okay, no peeking. What about the blockwise bit? How does that help efficiency?
Oh, this is clever. It's about how they process stuff within a single frame. Instead of one massive calculation for the whole frame, think of processing it in chunks or blocks. This blockwise structure lets the model do its diffusion sampling while also enabling, and this is key, efficient inference via parallel token generation within each frame.
Hold on. Parallel generation within a frame. But I thought it had to be sequential and causal. How does that work?
Yeah, it sounds contradictory, but think of it like assembling a really complex model kit. The causal rule says you must finish step 5 before you can start step 6.
Okay.
But blockwise means maybe step 5 involves attaching 10 different small parts. You could potentially have several workers' parts of the GPU attaching those 10 parts simultaneously, as long as they all wait until step 4 is fully complete before starting, and step 6 only starts once all 10 parts of step 5 are attached.
I see. So you're parallelizing the work within a single causal step, respecting the overall sequence.
Exactly. It lets the GPU process multiple pieces of the frame at the same time, which speeds up generating each individual frame, even though the sequence of frames itself stays strictly autoregressive, one after the other. It helps tackle those hardware inefficiencies by making better use of parallel compute power.
Okay, this is where it gets really interesting, right? The sources say NFD speed comes down to two big innovations. We've got the architecture, but what are the novel techniques? Let's get into the weeds here.
Right, this is the core of their contribution. The first one they talk about is extended consistency distillation. Now, consistency distillation itself isn't brand new. It existed for diffusion models.
Okay.
The basic idea is you train the model in a special way so it learns to jump from the initial noise to a high-quality output in just one, or maybe very few, sampling steps, instead of needing dozens or hundreds.
So it's like teaching the model a massive shortcut, skipping most of the slow refinement steps.
That's a perfect analogy. It dramatically cuts down the high computational costs associated with diffusion sampling for each frame. The NFD innovation here is that they extend consistency distillation to the video domain and adapt it specifically for video models.
Making it work for sequences.
Exactly. Getting this shortcut to work well for video, ensuring frames are consistent over time while still being super fast per frame, that's the tricky part. They engineered it specifically for their autoregressive setup, enabling efficient generation with just a few sampling steps.
Okay, innovation 1. Slash the cost per frame using a video-adapted shortcut. What's number 2?
The second big idea is speculative sampling. And this came from a really key observation, which the sources state very clearly. Adjacent frames often share the identical action input.
Right. If you're playing a game and holding walk forward, you hold it for more than 1/30th of a second, usually.
Precisely. So knowing this, what they design is a mechanism where the model generates next few frames using current action input. While it's busy finishing frame n, it basically guesses that the action input for frame n+1, n+2, maybe n+3 will be the same as for frame n.
It bets on the input staying the same.
Yes, and it proactively starts generating those future frames based on that bet.
Like getting a head start on your homework, assuming the assignment won't change.
Kind of, but what if the assignment does change? What if the user suddenly presses jump instead of walk? The sources say discard speculatively generated frames if the input action differs.
Okay, so if you guess wrong, you just scrap the work you did based on the wrong guess.
Correct. You throw away those speculative frames. But the goal, the benefit here, is to fully leverage parallel computation.
Right.
When the input is stable, which it often is for short bursts, the model isn't just sitting waiting for frame n to finish before starting n+1. It's already potentially churning out n+1, n+2, n+3 in parallel using that GPU power.
So even if you sometimes waste work, the time saved when the input is stable makes it faster overall.
That's the idea. It turns potential GPU idle time during stable periods into productive, predictive work. It's a smart gamble that exploits a common pattern in action-based video to maximize parallelizations. And crucially, that discard step means you always show the correct frame based on the actual current input. No lag or showing wrong predictions.
Okay, so we have extended consistency distillation, sampling, keeping the GPU busy predicting ahead. Two neat tricks. Did they work? How did they test this NFD model?
They evaluated it on a large-scale action condition video generation benchmark. That's pretty standard, basically, a big test data set to see how well models make videos based on commands like walk, jump, look left.
And the results, how did it compare?
According to the sources, NFD beats autoregressive baselines in terms of both visual quality and sampling efficiency. So better looking videos and generated faster than previous autoregressive attempts.
Better and faster, always good. But the headline number, the big achievement.
Yeah, this is the main claim. Right, abstract. We, for the first time, achieves autoregressive video generation at over 30 frames per second, FPS, on an A100 GPU using a 310M model.
Over 30 FPS, that's the benchmark, isn't it? The threshold for something looking like smooth, real-time video.
It really is. Hitting 30 plus FPS means it looks fluid, continuous to us. It feels real-time. And importantly, they did it with an autoregressive model, the kind we said is needed for interactive and streaming uses.
And they give the context, too. On an A100 GPU, which is a serious piece of hardware for AI.
Bian, yeah.
And a 310M models, 310 million parameters. That's substantial, but not completely astronomical these days.
Exactly. It's a decent size, capable of good quality, but not so enormous. It's totally impractical. Giving the hardware and model size makes the claim concrete. They showed it working at this speed on this setup, and claiming it as a first-time achievement for autoregressive video at this speed really highlights the breakthrough.
So pulling it all together, what's the big picture implication of this? For the field and maybe for you, the listener, down the line?
I mean, it suggests that those barriers to making truly real-time interactive AI applications with generated video are starting to come down significantly.
Right.
This pushes high-quality AI video from being mostly an offline, render-it-later kind of thing towards something that could be dynamic, live, responsive. It makes those futuristic ideas, the instant training sims, the live AI characters, the adaptive streams feel a lot closer to reality. It's a key enabling step.
Wow. Okay, so we journeyed through the challenge of real-time video, saw why autoregressive is the path for interaction, and then really got into NFD's two core innovations, that video-specific consistency distillation, cutting down steps per frame, and speculative sampling using prediction to max out the hardware. And it all leads to hitting that magic 30-plus FPS mark.
Yeah, it's a really nice example of how innovation on the algorithm side, the distillation, the speculation combined with smart architectural choices like that block-wise attention can really tackle these big performance walls. Getting over 30 FPS isn't just a metric, it unlocks the feeling of real time.
And maybe a final thought for you to take away. Achieving 30-plus FPS on a powerful A100 is a huge first step. But what comes next? How do you push this further? Can speculative sampling get smarter, maybe waste less work? And maybe the biggest question, how do you get this kind of performance on hardware that's, not in a giant data center? How does this reach more people?
Absolutely. Those are the next frontiers. This work shows it's possible on high-end gear. The next phase is optimization, refinement, and figuring out accessibility. They've opened a door. Now the work is exploring what's through it.
Great place to leave it. Thanks for breaking that down for us. And thank you for sending in the sources that let us dive into Next-Frame Diffusion today.